like Dr. Tosunoglu said, we're Team 2, and we're creating an educational robotics kit for high school students. The team consists of Carolina Padron, myself, Eric Fernandez, Gabriel Santos, and Dr. Tosunoglu. Here's an outline as to what we'll be talking about in the upcoming slides: motivation, design and analysis, global awareness, and impact. So there's a need and request from high school students and teachers for a robotics curriculum to be helpful for the students later on when they join the university and try to do a STEM major. With that said, we plan on creating a robotics kit that will help these students later on. We plan on making it low cost and have a dynamic curriculum. We hope to inspire these kids to join STEM majors.
So once we identified the problem, we actually started doing a lot of research behind it. Why these kids aren't studying STEM majors as well as other majors. So we actually found that for every job posting in the US, there was 3.6 unemployed people applying for that one job posting, while for every one unemployed person in the STEM major, there was 1.9 job postings. So there's plenty of jobs out there for these students that want to study and get into STEM. Only 30% of 12th graders who took the SAT are actually ready for college level coursework in science, which is kind of bad for our country. Basically, these kids are going into college and having to take remedial sciences, and they're just not ready for these curriculums. So there was a survey conducted asking teachers what the problems are, why they're not teaching these STEM majors. 30% of the biggest problem was lack of funding and research. You can see 20% was due to limited exposure to actual current technology. And then 12.5 said it was lack of training for the actual teachers. Not a lot of high schools can afford to hire an engineer to be teaching these kids about, the different fields. So our project, if you can see, wants to hit every single one of these points, keep a low cost, up-to-date technology, and have a dynamic curriculum which not only teaches the students, but also helps the teachers to be able to teach the course. We actually already visited a high school that has a robotics course. That was one of the problems. We found that they were lacking, actual structure and an actual curriculum. It was more of, go with what you feel, study different things every day, no actual structure. And we actually got a lot of positive feedback from the teachers and the students in creating this kit. We look forward to working with them in the future, and once we have a kit, some of the students actually signed up to test it for us and see how they can use it.
Okay, good morning. So for market analysis, we looked into various different robotic kits out there currently in order to evaluate their pros and cons. So first on the list is the EV3 Mindstorm by Lego. This is one of the most popular robotic kits for educational purposes out there in high schools. It retails for $350. It comes with 2 motors, 3 sensors, and several Lego pieces so you can build your own designs. The big downfall of this product is that the program is extremely simple, doesn't use real code, and it's fairly expensive. Now, some other alternatives we looked into are the Bags Robot, the Canon, the Finch, and the Hummingbird. The Bags Robot has a great curriculum and technology, but it's extremely expensive, as you can see, over $800. The Canon is a very attractive computer, but it only works for programming. Then the Finch Robot is a very small, really good priced robot, but it lacks focus on engineering and robotics principles. And lastly, we have the Hummingbird Robot, which is a very complete robotic kit for its price, but it lacks complexities and it's only targeted to small children. So as you can see, there are plenty of robotic kits out there in the market, but none of them really fulfills our needs. So that's why we decided to create our own design.
So this is our first proposed design. If you see, it's based off of a 4-wheel rover. There's 2 configurations for the wheels. You can put rubber inserts over each individual wheel and have them powered by 4 motors, or you can actually have the tracks on 2 of the outside wheels and have it only powered by 2 motors. So if you see, we've used 2 different levels to keep the robot as compact as possible. The bottom level would be for battery placement and additional sensors, while the top is for the microcontroller, the breadboard. And if you see, it has a bracket up here for sensor placement. The reason why we decided to put the microcontroller on top is to make it more easily accessible to the children, so they don't have to be, disassembling it when they make their tweaks. So we could make some improvements on it. We could add additional holes and some extra brackets just to make it, the sensor placement and motor placement and everything like that more modular. And also, the problem with the first design of the wheels is that you need 4 different motors and an additional motor shield for the microcontroller. So adding a slot on the rear to add a pivoting wheel, you could actually just have it powered by the front two wheels and just have one wheel in the back.
A second design alternative is to have the student create their own type of platform. They would be given different types of shapes, such as rectangles and triangles, and then they'd be able to create either a pentagon, a rectangle, any type of shape they would like for their own platform. Their creativity is the only issue which they should have. Anyway, so here is Gabriel.
Okay, so a microcontroller is nothing more than a scaled-down version of an integrated circuit board. But it's the most important part of the robot. We can call it its brain. So our team looked into different ones, and we nailed it down to three main candidates. We have the Arduino Uno, the Romeo, and the Raspberry Pi. So the Arduino Uno is very popular for robotics application. Main advantages are it's programmable in C and C++, it comes with a USB port, it's open source, has a huge community of support, and excels in hardware applications at a very low price. Then we have the Romeo, which is another microcontroller manufactured by a third-party company called FIU Robot, and it's based out of an Arduino board. So it pretty much has the same advantages as the Arduino Uno, but because particularly designed for robotics application, it has some added features. For example, it has 4 extra analog pins, it has 5 programmable buttons, a Bluetooth wireless connection, and 2 motor drivers, which is really useful for our project. Finally, we have the Raspberry Pi, which in itself is a fully functional PC, has more power, more speed, and more memory than the other two. However, it only sells on software applications and not so much for hardware. So after all this analysis, we decided that the Romeo by FIU Robot is the best option for our project. So after finalizing our design, we intend to conduct some engineering analysis on the structure. So first, we'll be doing thermal analysis in order to evaluate how the heat dissipation coming from the battery and the microcontroller affect the structure. Then we'll be doing a static analysis to evaluate the stresses, deformation, strains, and safety factors on the structure itself due to all the external forces acting on it. And then we'll also be doing some failure theory analysis, mainly on static loading, but possibly on cyclic loading as well. So here's the design flow for our project. So as you can see right on the top, we have the literature survey. After finishing conducting it, we'll come up to the right of the diagram where we're selecting the microcontroller and then the sensors and the motors. On the left side, at the same time, we'll be doing the structure engineering design, plus engineering analysis and simulations. Then, if we are not satisfied with the results, we'll go back and modify the design. If we are satisfied, we'll move on and build the prototype alongside with the other components. Then we'll be doing testing. For this part, we'll be doing 2 types of tests. Structural analysis, so we can compare experimental results with the ones obtained from the simulations, and some control theories based on some simple closed-loop feedbacks. For this, we'll be using an ultrasonic sensor to make the robot do some obstacle avoidance, an infrared sensor to make the robot make following a line path, and some temperature sensor to get a reactive feedback from the robot itself. Once again, if we are not satisfied with the results, we'll go back to the prototype and make some improvements. If we are satisfied, we'll move on, create a curriculum, and implement it on the high school. So as far as price is concerned, at this point, there's nothing really defined, but we can get a rough estimate of how much the components are going to be. So the Romeo is quoted at $30. Sensors tend to be between $5 and $15, while servos and motors tend to be between $10 and $50 depending on the material, the size, and the power. Jumper cables, breadboards, and other minor electrical components are fairly inexpensive. So if we sum all of this up, it will give us a rough estimate of $130, which then again will give us a budget between $100 and $150 to play around for the manufacturing of the structure.
So we actually looked at some standards for this. If you see, the first one is actually safety in the science classroom, how the kids can use the kit, how to stay safe, how to avoid accidents. The second one is actually for the supervisors and the teachers, what to do in case of emergencies, how to supervise the children, never leave them alone, things like that. The last one is actually toy safety standards. That one doesn't directly apply to us. It's put forth by Congress for toys that are aimed for children that are 12 and younger. But we do want to keep it in mind to make the kit as safe as possible and not have the kids have any accidents or anything with it.
Being from Florida International University, we're globally aware and we have a global perspective. With that said, 2 of the most common languages in the world are Spanish and English. So our curriculum will have both those languages. The robot kit will be low cost. It will also have different types of levels for knowledge. Some students are beginners, some are all the way to advanced, so we'll have both beginner to advanced. And C++ is the language we're going to be using. It is used in industries worldwide. We're going to address how to properly store and dispose of batteries. Here's our Gantt chart.
So basically at the end, what we want to have is we want to have a manufactured prepackaged robotics kit that's ready to go in the classroom from the beginning. We want to have it modular, we want to keep it safe, and we want it to be as cost effective as possible. A big emphasis on the engaging curriculum to teach these STEM principles. So basically we want the teachers, any type of teacher that's out there, whether she's a science teacher or just a regular teacher, go out there, use these kits and be able to teach the children how to use it. We want to keep it with the high school partnership, like you said, we want to test it out, see how the kids react to it and everything like that. And you know, we want to, in the end, to keep pace with new technologies and emerging technologies and, you know, help us become better engineers by getting feedback from the children and everything. Thank you.
Thank you.
Thank you.
Any questions?
Actually, that's a great idea, actually. So it's a very interesting concept. I have one observation that's not a big deal, it's not a criticism or anything, but on the first slide when you were talking about jobs, I had to really work it out a little bit because you had like one job, 3.9 people, and you have 1.9 jobs and one person. So
Yeah.
if you keep it one, same exact things, so that's easier to follow.
Okay.
Like one job, half a person, you know?
Yeah.
But the other, what about the questions is on the curriculum? I mean, how are you coming up with a curriculum? You have somebody helping you out with that, or because
Well,
we're not educators, so.
We're actually looking on.
With some of us are.
Dr. Tosunoglu is actually trying to help us out. He's in contact right now with someone from the education department. They're trying to see if they can actually send us a senior educational student to help us out with the curriculum, so kind of get their aspect on how to properly have an education curriculum for the children.
And how many kids per classroom are you thinking?
Well, right now that classroom had around, it was like 20 children. So we're trying to do this as maybe like an elective or something like that in high school, so keep it around that, like 20, 25 children.
One kid for 25 students?
Well, no. It would be one kid, I think it was like for five
Yeah,
students
five
we agreed on.
students.
Yeah, so it would be, you know, just a few kids for the classroom. You know, we could even expand it, you know, have one kid for 10 students and, you know, one of them could be programming while the other ones are setting it up and everything like that.
One last comment is, you consider, the final price you got there doesn't include labor or the metals or anything like that, that's just the
That's the
kit
office
components,
made
right?
of
Exactly.
The components.
You shouldn't worry too much about the cost itself, because you gotta compare, it looks like you're offering something nobody else is, so, you know, that's worth the money, so don't try to cram it down into a slight window and not be able
Yeah,
to
of
make
course.
it.
No, the reason why we put it there is because we still wanted like a rough estimate of how much it's going to cost to produce at least one unit, so we can have it in mind for later on. And yeah, we definitely want to try to keep it as cheap as possible, mainly because of the budget for the different schools. But from there on, we just want to make it focus on the efficiency and the product itself, and then not so much the price for the first product.
Which school was it gonna be?
Archimedes Academy, it's in South Miami. It's a private school, but they have actually very
They
good
just started a
robotics.
robotics
Yeah.
curriculum program, and so they're not really structured yet. So we hope to accomplish that.
The reason I asked the question, because FIU is in partnership with a couple of schools that have robotics in their curriculum. Give you the names, Northwestern and Booker T. Washington. So there are real guinea pigs there that you may want to tap into, and they're in partnership with FIU on what's called the education effect. So do some research on that, and that would be a good resource to tap into. Now, regarding your testing, you seem to be emphasizing a lot of static testing, even though a robot is a pretty dynamic piece of device, which means that it's always vibrating, and parts could work loose because of that vibration, as well as you could have fatigue failure because of vibration. I don't think you put enough emphasis on that. You may want to reconsider that and make sure that you're not just concentrating on static loading, but also dynamic loading, so you can deal with all of those consequences from the dynamic loading. Does that make sense?
Yes.
Yeah,
All right. Those are my comments.
Could you go back to that design flow slide?
Sure.
In your presentation, when you were talking about the conducting structural analysis, looking at theory versus experimentation, when you talk about if you're satisfied, then you go to the implementation
Yes.
part of it.
Well, when,
What's your criteria for satisfied? I mean, what do you be looking at to make you move on to that next phase?
Oh, okay. We're looking at the simulations. At the end of the day, it's just a simulation. So
Mhm.
there could be a lot. That's an ideal scenario. So once we actually test the structure and put everything together, we obviously do not expect to have those same results, but at least have some similar results, because that's the reason why we designed that structure in the first place, because we're agreeing with those results we were getting. So maybe like the safety factor was at a specific range that we agreed with, and then we tested it, and maybe it wasn't that, as high as we wanted it to be. So now we have to reconsider and make some improvements.
So you're gonna have a particular range that you're gonna be looking at.
Yeah, of course.
That range is going to be something that's equal to that's in the literature that's acceptable.
Yes,
by
that's it,
most
yeah.
people.
I don't want to say any specific number right now because it's just the design and we still don't know exactly what type of numbers we're expecting to get for every single test. But once we can perform the simulations, we can get a better idea of what to expect for both the experimental and the theoretical ones.
But you have a list of criteria that you'll be looking at that you're going to base that decision.
Yes.
Yes.
One of the big ones where we actually noted was that toy safety standards. Since it doesn't directly apply to us, since it's 12 and under, but we do want to keep it in mind. So they have a specific set of standards as to how safe the toy has to be, how much, loads and everything it can take so children can play around with it and not have components break off and become dangerous or anything like that. That's something we're looking at.
I mean, it looks like this will work in junior high as well, so why not?
There is actually another team doing a specific design for the middle school because this one's geared towards high school students. That's why we're using like the C++ code and stuff like that. So we think that might not be, might be a little too complicated for middle school.
Okay.
So there's another team geared towards the younger students.
Okay, I'm up. May I suggest in the future, when you make presentations like this is a great flow chart, but you have a lot of content on your slides, and it's very difficult for us in the audience to choose between reading what you have up there or listening to you. We always want to listen to you, so I suggest that you compact what you have on your slides and not contain and read verbatim. Just give a couple of bullet points. We'd much rather hear it from you, okay? The second thing is you had a slide up there where you were comparing basically your market analysis of what's out there. You gave a price. May I see that slide, please?
Sure.
You gave a price and the advantages and disadvantages of the various units. What I would have liked to have seen is the end of your presentation is put yours on the board. I'd like to see your fifth one where you hope your price is going to be. I want to know why I'm going to buy yours over these, because in the end, you may come out with a good price, but you're losing features. So I would have liked to have seen a whole
Comparative.
by me, okay? That's what I'd like to have seen. And I do agree with this gentleman's comment. I'm sorry, I've not. I would have liked, when you put this price up here, to estimate at least labor, packaging, instructional manual that you've got to print and go out with this. So it's not just, it would be lovely to sell for raw product components, but nice presentation.
Thank you.
Thank you.
I have an additional question. I don't remember the details of the standards that you were trying to comply with. Can you bring that slide back up, please? Do you believe that that is comprehensive enough, standard related to a robot design in an educational environment?
Well, the reason why we put these, I mean, we actually just put for science, and you know how to deal with the children and stuff like that, especially from an educational standpoint. So we want to be able to sell these to schools, so we want to concentrate on the science behind it and everything like that, and the safety for the students and the supervisors.
What about O&M issues? Operations and maintenance issues?
Well, we have, I mean, these are just the major standards that we put. We have more standards that are actually just listed in our report. So maybe we should
Maybe
include them
say
all
other
here.
standards, okay,
Yeah.
just to cover your butt.
Yeah.
All right, okay, thank you.
Any other questions?
Well, all the comments were right on actually. I mean, you know, we need to incorporate those. And we would like to see the fifth column in November. When
Yeah,
there's
that's what
final
I said, it's still
presentation.
very preliminary.
Those are very good comments. So thank you for that, and thank you to the team.
Thank you very much.
Thank you.
And,